Welcome. So we are coming to the next part of our course. We are going to look at what happens when we don't have a well mixed behavior or a plug flow behavior. In your undergraduate course, these are the two extremes that you had considered. One case was a well mixed reactor where concentrations were everywhere the same. Other case was a plug flow reactor where concentration was changing with respect to location, with respect to the entry to exit of the reactor. So these are the two idealized cases. Now what we are going to look at in this part of the course is what happens when either of these extremes are not met, because these are idealistic situations, they are not real life situations, so to say. So this is what we are going to look at in this part of the course. So just to get you started, uh, let's quickly see where we are in the course. uh, this is where we are in the course with respect to our overall course. We have done revision of our basic concepts, we have done real life reactors, we have done this in great amount of detail, multiple steady states, stability, and so on and so forth. This is where what we are going to do now. How do we characterize real life reactors which are not completely well mixed nor are they completely plug flow? How do we, what is the cause for the first of all deviation from these idealized behavior, and how do we characterize them, and how do we use it for our design purposes? That's what we are going to do in this part of the course. Just to quickly get you to revise, what are the two time scales in exothermic batch reactor that we talked about in our previous lecture, and how does generation and removal of heat determine reactor safety, whether it is in terms of a plug flow reactor, whether it is in terms of a well mixed reactor, or whether it is in terms of a batch reactor. How does this heat removal rate and heat generation rate determine what in terms of temperature profile, and how these affect, or how these need to be taken into account for safe design and safe operation of the reactor. That's what we have done in this course so far, just to get you to revise, and then we will go forward. Okay, so let's go forward in terms of this lecture. First of all, think about tubular reactors operating at different velocities, having different L by D ratios. Remember, in the second lecture, we designed plug flow reactors where we had, let's say, 2-inch diameter pipeline. In one case, it was kilometer long length. In one case, it was 1 meter, 2 meters of that order, or few meters of length. So, couple of questions I would like you to think about. At what velocity does the reactor, having a tubular reactor, let's say, behave like a plug flow reactor? Okay, whether velocity should be 1 meter per second, whether velocity should be 10 meter per second. If you can think in terms of Reynolds number, whether Reynolds number should be 100, 1000, 2000, 5000, 10,000, 20,000, 100,000, when will we get a plug flow behavior? How do I characterize that plug flow behavior? Another thing could be in terms of L by D ratio. L by D ratio could be thousands, lakhs. L by D ratio could be hundreds. L by D ratio could be 10. L by D ratio could be 5. What I'm trying to say is, suppose our reactor is like this. Let me just quickly draw something so that we are able to visualize what we are talking about. When we say L by D ratio, what I mean actually is, suppose a reactor is like this. Let me draw neater reactor. Suppose a reactor is like this. Very long. Let's say L by D is 100. Right? It is just, I'm not drawing L by D equal to 100. I'm just trying to say that this is a very long, length is very large as compared to diameter. Okay? Or reactor is like this, like a disk if you want. Right? Or a reactor is like this. L by D is very small. They could have same residence time, Will this behave like a plug flow? Will this behave like a plug flow? Will this behave like a plug flow? When do we say that a reactor behaves like a plug flow? And whether velocity is one Reynolds number, if you want to think in terms of whether Reynolds number is 100, 500, 1000, 10,000, 20,000, when is it that we say that the reactor behaves like a plug flow reactor? Okay. So what are the characteristics? What I want you to think about is what are the characteristics that we need to consider when we say a plug flow reactor. Okay. Okay, let's go forward. Same way, think about a well mixed reactor. Imagine that there is a well mixed reactor like this. Let me just put this. Imagine that there is a reactor like this. Right? This is a reactor. There are impellers here, agitators. We've seen that in our second lecture. Flow comes in, flow goes out. Maybe jacket is there, jacket is not there. That's not important just now. When we say well mixed reactor, what we mean is concentration everywhere inside, whether it is here or 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 here, is the same. Concentration is the same, and therefore it is equal to the outgoing concentration. Suppose we think about this reactor and we say that we want to operate this reactor impeller, operate this impeller at, let's say, 100 rpm, 100 revolutions per minute, or 50 revolutions per minute, or 500 revolutions per minute. So at what rpm will this reactor behave like well mixed reactor? What is the liquid volume? So if I fix an impeller speed, let's say 100 rpm, what liquid volume and what arrangement of impellers do we need so that it behaves like a well mixed reactor? Whether if I take 100 rpm impeller, say pitch turbine impeller, one impeller 100 rpm operating at 100 rpm, let's say 1 meter diameter impeller, what value of liquid volume, say should it be 1 meter cube reactor, 10 meter cube reactor, 100 meter cube reactor, will all of them behave like well mixed reactor if I have the same impeller operating at same rpm? So what I want you to think about is what is the physical meaning of well mixed behavior. That is, right now in this lecture we are going to look at it little bit qualitatively, little bit quantitatively, but later on as we go along in subsequent lectures we will do more and more quantitative assessment. So first of all, I would like you to think about qualitatively, what do you think are the characteristics which makes a particular reactor plug flow or a particular reactor well mixed? Can we write down characteristics, say 1, 2, 3, 4, 5, 6, 7, 8, 9? These are the characteristics, these are the things that is required to make it a plug flow. These are the things that is required to make it a well mixed reactor. That's what I want you to do. Write down in, pause the video, write down in your notebooks. These are very important, although you may write it qualitatively, but now we are slowly going to quantify all these things. That's why I want you to write down qualitatively first. Okay, let's go forward. Okay. So if you recall from your undergraduate lectures, when you say plug flow, what you would mean is that the fluid inside the liquid inside the reactor behaves like a plug. That means if this is a plug, this whole plug moves to the right from entry to exit. Okay? Entry to exit, as if it is like a piston going from one end to the other. Visualize a cylinder and a piston. So fluid behaves as if it's a piston. So sometimes in old textbooks you might find it is called as a piston flow, but the modern nomenclature in most of the textbooks and most of the universities and most of the places, it will be called as a plug flow. Okay, it goes from entry to exit. Couple of questions I want you to think about. One is, what does it mean in terms of mixing in the radial direction? Now recall that, remember that this is a pipe. This is a pipe. This is a pipe. So this direction along the axis, along the center line, this direction is our axial direction denoted by Z. If you look at it from the side, if you look at it as an end elevation, oops, better. Radial direction is away from the center, radial direction. Okay? And tangential direction is around the axis theta. Cylindrical coordinate system. You would have studied all this in your undergraduate course. So what I want you to think about is, what does plug flow behavior mean in terms of mixing in the radial direction here, and what is the cause of mixing in the radial direction? Why is there a mixing in the radial direction, and how do we quantify mixing in the radial direction? Okay. Second thing is, what does it mean in terms of mixing in the axial direction? Mixing in the axial direction. What is the cause of mixing in the axial direction? And how do we quantify mixing in the axial direction? Think about these answers, write these answers for yourself. So when we say plug flow, piston flow, right, that means all the fluid elements that are at different locations in the radial direction, they move at the same velocity and they spend same amount of time in the reactor, and there is no different, and the concentration here at different locations in the radial direction is the same, otherwise we would have had to worry about concentration, how much time this particular fluid spends, this particular fluid spends, this particular fluid spends, and so on and so forth. So concentration at different radial locations is the same, concentrations is the same. What does it mean in terms of mixing? That if I put some material here, if concentration is to become the same in the radial direction, this mixing should be fast or slow? Yes, this mixing should be very, very fast or rapid mixing in the radial direction. Rapid mixing in the radial direction. So when we say rapid mixing in the radial direction, what does it mean? That whatever concentration I put, let's say I put some reactant here, that reactant mixes very, very fast in the radial direction. Okay. Now, what is the cause of mixing and how do we quantify mixing? That's what we are going to look at. In terms of axial direction, that if I put some material here, if I put a reactant here, does it mix in the axial direction? Does it mix in the axial direction? If I put some reactant here, does it mix in the axial direction? So when we say plug flow, it means no mixing. Fluid element that is at the start of the reactor somewhere here is not at all mixing with the fluid element which is maybe, let's say, ahead of it. Okay. Imagine as if you are going in a corridor and everybody is walking at the same speed. Several of you are walking in the corridor and they are all going in the same speed. So there is no mixing that will happen between students or between several of you that you are walking. But at the same time, radially perpendicular to the flow, mixing is very, very rapid. That's the meaning of plug flow. So we'll quantify that. One way to quantify that is to write conservation equation consisting of two parts, convection and dispersion, in a control volume. So you have done this in your undergraduate course. Okay. I'm just trying to remind you of the different things that you have done in your undergraduate course. So imagine this is a control volume, small element of size delta x, delta y, delta z. So we can write convection coming into this control volume and turbulence causing a flux of A into this control volume. So diffusion, molecular diffusion, as well as turbulent dispersion. Now we are using two different words. We are using the word diffusion. So we are using this word diffusion. By this word, what we are meaning is the molecular diffusion, molecular motion. If some of these terms are not clear, you go back to your undergraduate mass transfer lectures or wherever you have studied all these and revise those concepts. Second thing we are talking about is dispersive. Dispersive meaning turbulent motion, turbulent dispersion. So just like diffusion, we characterize by diffusivity, and sometimes it is also called as diffusion coefficient. This dispersive transport, because of turbulence, we are going to call as dispersion coefficient. We could have also called it as dispersivity, but that's not the word that is used. We use the word dispersion coefficient. Remember, when turbulence is there, you have eddies going from one place to another place, and they take momentum or heat or mass, in this particular case the species A, from one location to another location. That is the cause of dispersion. So think about all this, revise your undergraduate lecture if you don't recollect some of these things. If you don't recollect some of these things, and go forward. So if I want to do material balance for A over this control volume, what we have to do is write a equation for entry and exit of A. So if you think about the left phase, the rate of entry of A by way of convection is concentration of A multiplied by the volumetric flow rate. Volumetric flow rate is nothing but velocity multiplied by delta y, delta z, area of this particular plane. If we are thinking about A leaving from the right phase, this pink arrow, it will be concentration of A multiplied by volumetric flow rate through the right phase. It will be velocity multiplied by area of that right phase, area perpendicular to the velocity. This delta y, delta z. Same way, entry of A in the y direction, because of velocity in the y direction, this pink arrow. It is concentration of A multiplied by velocity in the y direction multiplied by area perpendicular to the y direction, which is nothing but delta x, delta z. Same way, A will be leaving through the top phase, this pink arrow. Rate at which A leaves will be concentration multiplied by volumetric flow rate. Volumetric flow rate is nothing but velocity in the y direction multiplied by area perpendicular to the y direction. That is the area of this top phase, delta x, delta z. Through the front face and the back face, this pink arrow is bringing A in because of convection in the z direction. The rate would be concentration of A multiplied by volumetric flow rate in the z direction, that is nothing but Vz multiplied by area perpendicular to the Vz, area of the back face, delta x, delta y. Same way, A leaving through the front face, Ca multiplied by Vz multiplied by delta x, delta phi, this pink arrow. So this is the rate at which A comes in because of convection. This is the rate at which A leaves because of convection. So in minus out. Same way diffusion or dispersion, we can call it as flux of A, and A in the x direction, flux of A in the x direction multiplied by delta y delta z, flux multiplied by area. That will give you the rate at which A comes in because of diffusion and dispersion. Similarly, from the right phase, NA at x plus delta x multiplied by delta y delta z. In the bottom phase, NA in the y direction, delta x delta z at y. The top phase, NA in the y direction multiplied by delta x delta z at y plus delta y, top phase. NA in the z direction multiplied by area of the back phase, delta x delta y at z, minus NA in the z direction, delta x delta y at z plus delta z. So we have, these are all the incoming terms which bring A because of diffusion and dispersion, terms which take away A because of diffusion and dispersion. So in, out, plus A could be generated or A could disappear in this control volume by way of reaction. A might be a reactant. So then we are just going to write it as source term. So the source could be, it could be a sink also for A, or it could be source also for A. A is, if A is a product, then A is generated in the control volume. So S is the generation rate per unit volume. Or if A is a reactant, it is disappearing in the control volume. It is reacting. Disappearing in the sense it is reacting. So S could be sink of A. Again, sink per unit volume. Right? The rate at which A is generated or A reacts per unit volume multiplied by the volume of the control volume. So what this S means, it is either sink or source. S is, if it's a reactant, it is a sink, and it is a rate at which A reacts. It is negative, right? KCA, negative KCA, right? It is disappearing. If A is a product that we are writing, it is source. It is rate of generation of A. It is generated. Okay. It is kilomoles per meter cube per second, rate of generation multiplied by the volume. And same way this concentration, if you like, concentration is kilomoles per meter cube multiplied by volumetric flow rate, meter cube per second. Right? This will just cancel out. Is the rate at which A comes in, rate at which A leaves. Flux now, NA is kilomoles, it is flux, kilomoles per meter square per second multiplied by area, meter square. Right? So it is flux of A multiplied by area, rate at which A comes in by diffusion and dispersion, turbulent dispersion. In, out, generated or reacted must be equal to accumulation. Accumulation is nothing but change with respect to time of the total number of moles that are there of A in the control volume. That's nothing but concentration multiplied by volume. So that's our accumulation. Okay. So if you divide throughout by delta x, delta y, delta z, take the limit as delta x, delta y, delta z tending to 0, you can simplify. You have done this in your undergraduate course. Right? Pause the video, do it for yourself. Here is the equation. So this flux of A we can write using Fick's law, right? So Na we can write as diffusivity multiplied by dCA by dx. So remember, the flux we are writing in the x direction, Na in the x direction. If it is molecular diffusion, we would have to write Fick's law as molecular diffusivity multiplied by dCA by dx. If it is turbulent diffusion, we would have to write it as minus turbulent diffusivity or dispersion coefficient into dCA by dx. Right? And we are just combining. So both fluxes, it could be turbulent and dispersion. We have to say Na in the x direction is minus molecular diffusivity plus turbulent diffusivity into dCA by dx. Now, usually this molecular diffusivity is very small, flow is turbulent. We want flow in the reactor to be turbulent for good heat transfer, good mass transfer, and so on and so forth. So, turbulent diffusivity is far, far greater than molecular diffusivity. So much turbulence is there, eddies are there, take away mass of, they take away A from one location to another location at a very high rate as compared to molecular diffusion. That's why I've written only the turbulent diffusion part, turbulent dispersion part. See, we are using these words interchangeably. Sometimes we call it as turbulent diffusion, but we should really be calling it as turbulent dispersion. Diffusion is something we reserve for molecular motion, molecular transport. So if you simplify, you will get this equation. You will get this equation. I can write it in the vector form. dCA by dt is Vj del Ca by del xj dt des d square Ca by dxj square del xj square. So we are writing it in the vector notation. J is a vector notation. J is going to take three values x, y, and z. Okay. And xj is going to be x or y or z. Okay. And same way here, xj here is going to take three values x square, y, del y square, or del z square. So if A reacts in the control volume, let's say reaction is first order, S is a sink, disappearing. It is minus K into Ca. Okay. So we can write this in a simplified vector form. Let's go forward. So imagine now this reactor we have. Let's say it's a tubular reactor. Let's say V is the velocity, average velocity. D is the diameter, L is the length. Now we can make things dimensionless in this equation, or we can simply say what is the convection time scale for mixing? It is L by V. Convective mixing rate would be V by L. Dispersive time scale for mixing is L square by dt. L square by dt in the axial direction. Dispersive mixing rate is dt by L square in the axial direction. Axial direction. Recall, if you are not comfortable with these, revise your undergraduate course, mass transfer, time scale for mixing by dispersion, time scale for mixing by diffusion. All these things are there in undergraduate course. So ratio of convective to dispersive mixing rate is nothing but V by L and dt by L square. I can simplify this and I will get LV by dt or VL by dt. We call this as Peclet number. So the Peclet number is a ratio of convective mixing to dispersive mixing rates. So when Peclet number is far, far greater than 1, what do we mean? That axial mixing is negligible. Peclet number is far, far less than 1. What do we mean? Axial mixing is significant. Again, Peclet number far, far greater than 1. What does it mean? Practically, dispersive mixing rate is negligible. Dispersive mixing in the axial direction is negligible. Dispersive mixing in the axial direction is negligible. It's only convection that is dominating. So Peclet number greater than 1 means only convection is occurring, no mixing is occurring in the axial direction. Okay. And Peclet number far, far less than 1, which means dispersive mixing rate is very, very high. Dispersion, which causes mixing in the axial direction, is very, very high. It is much higher as compared to convection. So it will be mixed in the axial direction. In the radial direction, there is no convection. Velocity in the radial direction is 0. Look at a velocity profile. Velocity profile is from left to right. If you want to draw a velocity profile is like this. Turbulent velocity profile, right? There is no velocity in the radial direction. This is not there. There is no velocity in the radial direction. So there is no convection. And dispersive rate of mixing would be turbulent diffusivity divided by d square, diameter square, or time scale would be d square divided by dt. Time scale for mixing in radial direction. So what do we want for plug flow? Ratio of dispersive mixing in the radial direction to that in the axial direction should be far greater than 1. So that means if I write dispersive mixing in the radial direction, that's dt by d square, and dispersive mixing in the axial direction, that is dt by L square, this ratio should be far greater than 1, which means this L by d should be far greater than 1. L square by d square should be far greater than 1, or L by d should be far greater than 1. So when we say plug flow, what we mean is that Peclet number should be far greater than 1, and L by d should be far greater than 1. Peclet number far greater than 1 will ensure that there is no axial mixing. L by d is far greater than 1 will ensure that radial mixing is very rapid. Right? Both these conditions are required. Only then we will have a true plug flow. Right? That's what this means. That's what I've just written that in the slide just for your understanding. We've talked about it. Okay. Velocity profile is nearly flat. Why? Because we want every fluid element to spend the same amount of time. That will not happen if flow profile is laminar. If flow profile is laminar, parabolic profile, right? There is a wide variation of velocities. So different fluid elements that are here or here or here or here, they will spend different amounts of time. It's not like a piston flow. Only when it is turbulent flow, which means velocity profile is practically flat, which means velocity is the same at all radial locations, then only all fluid elements will spend the same amount of time. Packet of fluid, piston flow. So third condition that is required, one is Peclet number far greater than 1, L by d is far greater than 1, and flow is highly turbulent, which makes velocity profile nearly flat. Vz is not a function of r, or practically not a function of r. It's still a function of r because of no slip condition at the wall, but it is practically not a function of r. That's what will ensure plug flow behavior. So these three conditions are required. Next, think about a well mixed reactor. What is the residence time in the reactor? It is volume divided by flow rate. Now this impeller is going to cause mixing. What do we want? If concentration everywhere is to be uniform, the mixing generated by the impeller should be very large as compared to residence time. So well mixed behavior will occur when residence time is far greater than mixing time. Think about all these things, visualize, right? Mixing time by the impeller, you might have studied in the undergraduate course, is volume of the liquid divided by flow rate generated by the impeller. Flow rate generated by the impeller will be NQ, pumping number of the impeller, flow number of the impeller, multiplied by ND cube. So for well mixed behavior, we want V by F to be far greater than V divided by NQ and D cube, or NQ and D cube should be far greater than flow rate. That means the flow generated by this impeller mixing flow generated by this impeller inside should be very, very large as compared to, if let's say it's a downflow impeller, it will generate this kind of pattern. So the mixing generated or flow generated by the impeller should be very, very large as compared to the flow rate. Only then concentration at all locations will be the same, and it will be the outlet concentration. That's what will go out. Then we can ensure well mixed behavior. So such thing will happen at high impeller speed or high flow number impellers, or you use multiple impellers to generate mixing throughout the liquid. So if your vessel is like this, if your vessel is like this, and I just have one impeller rotating like this here, it will generate mixing, but it will generate mixing only here. Will the concentration here, 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 here be the same as concentration here? May not be, definitely not. And flow is coming in here and let's say going out here. So mixing has to be ensured. So I will need multiple impellers to make sure that liquid is completely well mixed. Even these corners are well mixed, right? Corners are agitated nicely, mixing happens, right? So we have to ensure that high impeller speed, we have to ensure high flow of the impellers, and we have to have multiple impellers to ensure that there are no dead zones. When you say dead zone, there are dead pockets, like as if the mixing is happening here but no mixing is happening here. That should not happen. Means all zones or all liquid should be mixed, right? So number of impellers, what type of impellers, how much flow is there, how much impeller speed is there, all those things will decide whether this condition is satisfied. Mixing time in the vessel should be far, far less than residence time. If the situation is like this, if the situation is like this, only one impeller here, small impeller here, then this part will be well mixed. This part will be nicely agitated, but there is no mixing between, say, liquid that is here and liquid that is here. So mixing time would be large. We can determine mixing time experimentally. Just to Google, how do I determine mixing time? Right? So that's what we mean. Mixing time should be far, far less than residence time. And how do we ensure good enough impeller speed, high impeller speed, good flow generated by impellers, and good number of impellers to ensure that all liquid is mixed with each other, not just some parts of the liquid are mixed. That's the meaning of well mixed behavior. Okay. So how do I characterize now all this? All this is characterized by this equation, our conservation equation for the tracer. So now if there is a reaction happening, there are three options with us. One is to measure the velocities and turbulent diffusivity at all locations and solve this PDE and get a concentration profile with respect to time XYZ. And that's what we have. We can calculate conversion, right? Or we can predict velocities using computational fluid dynamics, predict velocities and turbulent dispersion using computational fluid dynamics, and then solve this PDE and calculate concentration of A at locations, various locations, as well as with respect to time, and we can calculate conversion between entry and exit. Or third, we give a stimulus, we give an input to the reactor and see how the reactor responds and compare with plug flow behavior or compare with well mixed behavior. This is what we call as our, let me just This is what we call by our residence time distribution. This is what is involved in our residence time distribution. We give some stimulus or we give a disturbance to the reactor, see how it behaves, and check whether it behaves like a plug flow or well mixed or something in between. This is what we are going to do in the course, but this is what people do nowadays. People don't do RTD, people don't do this kind of response behavior. I'll tell you the reason why not. But with computers, you can either predict and you can measure advanced measurement techniques, and you can actually solve, and you can get concentration at all locations. So you can actually calculate, if you do computational fluid dynamics and coupled with measurements, you can actually calculate the concentration at all locations in the vessel. You can calculate, you can compute concentration at different locations. You can compute the concentration here, 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 everywhere. And then you can find out what is the rate of reaction here, 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 what is the rate of reaction here. And then add up all those. That together will tell you what is the total rate of reaction, and that will decide your concentration of A going out. Conversion you can calculate. Okay. Right? So this is what we are going to do in our subsequent lectures. Okay. If you want to just read up more, this is where we are. We are in terms of if you are referring to Fogler's book, we are on chapter in 4th edition. We are on chapter 13. Corresponding chapter in 5th edition is chapter 16. So we will stop the lecture here. I've just given you a background of what is meant by well mixed reactor, what is meant by plug flow reactor, and we are going to now characterize all of that and use it for design, use it for calculating conversion and so on. Okay. Let's stop this lecture here.